let's now talk about uncountable sets. So theorem 8.7.1 in the notes says that the interval from 0 to 1 is uncountable. So by the way, actually, I don't think I ever introduced this terminology yet exactly, but this just means not countable. So if something is not countable, we say it's uncountable. Okay. And by the way, the notation is kind of unfortunate, right? Remember when we were doing the Cartesian product, we had like pairs of numbers, right? This doesn't mean the pair of numbers 0, 1. This is the set of all x such that x is between 0 and 1. This is an interval, but yeah, it has the same notation, right, as a pair. Okay. Okay, so we want to prove that this interval does not have the same size as the naturals. Oh, well, first of all, okay. I mean, one trivial thing is this is obviously not finite, right? Remember, like to be countable, you can either be finite or you can have the same size as the naturals. Obviously, this is not finite. So all we're really asking here is, does it have the same size as the natural numbers, the same cardinality? So what we're really asking is, does there exist a bijection from the naturals to 0, 1? So let's do this by contradiction. So I want to prove that no bijection exists. And let's do it by contradiction. So by contradiction, so suppose that f is a function from the naturals to 0, 1, so is a bijection. So if we're doing this by contradiction, so I'm assuming this is a bijection, and at the end we want to get a contradiction. So we want to basically derive some sort of nonsense from this, which will tell us that clearly this f could not have existed, because if it exists, it leads to a contradiction. For every natural number n, if I take f of n, well, it's a number between 0, 1 and 1. So is a real number between 0 and 1. So it must have some type of a decimal expansion. So let's write out the decimal expansion of f of n for every n. So let's look at f of 1, for example. So since f of 1 is a number between 0 and 1, the decimal expansion has to start with like a 0 point something, right? So f of 1 is 0 point, something, 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 blah, 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 where all of the digits are between 0 and 9. So, so I'm going to write out the digits as D11, D12, D13, D14, and so on. So each of these digits is a number between 0 and 1. By the way, some numbers have kind of a finite decimal expansion, like if you take 0.5. But if you have 0.5, you can always write it as 0.5, 0, 0, 0, 0, 0, 0, 0, 0, 0, off to infinity. So actually, really, you can always write an infinite decimal expansion for any number between 0 and 1, right? So yeah, if it's 0.3, you write 0.3, 0, 0, 0, 0, off to infinity. Is it clear what this notation means? So I'm talking about the first decimal, second decimal, etc. Right? And then you can write out f of 2. It's going to be 0 point, let's say, some number d21, d22, d23, d24, etc. So f of 3 is d3, 1, d3, 2, d3, 3, d3, 4, etc. And let's say f of 4, so I'll stop at 4. But, this goes on forever. So 4, 2. Okay. Is it clear what I'm doing here, or any questions about this? Okay, so these are numbers between 0 and 1. They have a decimal expansion. Now what I'm going to do is, so the way I'm going to get a contradiction is by trying to show that this function f, so we're assuming f is a bijection, and I want to show that this function f was not surjective, which in other words means I want to pick a point between 0 and 1 such that it is not in the range of f. So if I can find just one element of 0, 1 that's not in the range, then I'll be done, right? That will show that it's not a surjection, therefore it's not a bijection. So here's how I'm going to come up with this number. So let x be the number with the following decimal expansion. So x is 0.x1, x2. Well, maybe I should have said here, actually, before I do this, just to be clear, all of these dij's, so that's the jth decimal of f of I. These are all numbers between 0 and 9, right? Okay, so what I'm going to do is let x be 0.x1, x2, x3, ... where the way I define x, each decimal of x is as follows. So xi is going to be equal to 1 if dii is even, and 2 if dii is odd. Okay. So basically I look at so I take my function f, I look at f of 1, and I just I look at the number d11. If this is even, then I make the first kind of decimal of x, I make it a 1, and if it's odd, I make it a 2. I then look at the second one, and based on that, I define the second decimal place, the third one, the fourth one, etc. So this is going to be a number between 0 and 1, right? It's going to be like x is going to be 0 point something, 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 where all of these somethings are either a 1 or a 2. So it's like 0.111, 222, 12, 12, 22, 1, some kind of a string of 1s and 2s. And like any number like that, it's a number between 0 and 1, right? So x is between 0 and 1. And so the claim is that there's nothing, no function, no element of the naturals maps to x. This all is a bit abstract, I think. So, I mean, are there any questions at this point? Or does this seem weird? It's kind of weird, right? Well, okay, so what I want to show is, so claim there does not exist a natural number, let's say, natural number n such that f of n equals x. So suppose f of n is x. So for some, suppose n is a natural number such that this holds. So can anyone see why this is impossible? Yeah? Oh, so say it again? Yeah. So basically, look at f of n. You know, f of n is, I don't know, dn1, dn2. Like it's an infinite, well, it has some sort of decimal expansion. If I look at the nth digit of f of n, so here's how, so look at the nth digit of f of n. By definition, it is dnn, right? So, I mean, that's how I define dnn. It's the nth digit of f of n. And if this is odd, then, so if dnn is odd, then the nth digit of x is 2, because that's how I defined x. But then 2 is not odd, so then they must be different in the nth digit. And conversely, if dnn is even, then the nth digit, so kind of the point of 2 here is that it's even, right? So then the nth digit of x is 1, which is odd. So no matter what, f of n and x have a different nth digit, so they can't be equal. So that proves the claim, and that actually proves the whole theorem, because so the claim implies that f is not surjective, which is a contradiction. Which is what we were aiming for. So if you didn't really understand the construction of x, maybe it's good for me to just throw in some example numbers, and we can kind of see how you would construct x. So, right? So, what's your favorite number between 0 and 9? Anyone?
5.
5. That's a good number. Anyone else?
7.
7. Okay. How about an even one? That's a good one. I'll do 0. Okay, so just to kind of, so this is kind of taking a step back to this part of the proof, but so in case you didn't really understand how to define x, this is kind of a specific example, right? So imagine f of 1 is some number like 0.5 something something something, and f of 2 is like something 0 point something, and then the second digit is a 7, and then we don't really care about the other digits. Suppose f of 3 has the third digit equal to 2, and f of 4 has the fourth digit equal to 4. Then what I would do when I'm defining x, I would say x is equal to 0 point. I look at the first digit of f of 1. It's a 5, which is odd, so I write 2. Because if d11 is odd, I write a 2. d22 is odd, so I write a 2 again. This one's even, I write a 1. That one's even, I write a 1. And you just continue this process, right? You can just keep looking at the diagonal entries, and based on what it is, if it's odd or even, you either write a 2 or a 1. And the point is that the number you write, it can't be equal to f of 1, because the first digit of f of 1 is odd, but the first digit here is even. Like we always switch evens to odds and odds to evens. So like x is not equal to f of 1. I mean, this starts with a 5, so it's definitely not equal to that. If you look at, for example, f of 3, okay, that has a 2 in the third digit, but because 2 is even, we made the third digit odd. So it's not equal to f of 3 either. And the point is, it's not equal to any of these things, but therefore f is not surjective, because this is in the codomain, but it's not in the range. All right, any questions about this? So this is an important trick to kind of master here, because yeah, this is kind of the main way of proving something is not countable. Okay, so let's kind of talk about a few ways of showing something's not countable. So this is kind of the main way, but there's other sort of cheap, well, there's another cheap trick as well. So, I mean, so to show a set A is uncountable, well, one kind of, I mean, something easier would be to show it has that A has a known uncountable subset. So right now I've only shown one thing is uncountable, but you know, for example, so this is what we just showed was uncountable. But also, I think in your assignment you showed that things like if you take an infinitely long open interval from like, what is it, negative infinity to A or something? Was that the question? I don't remember, but then it has the same cardinality as 0 to, you know, the interval 0, 1. So for example, yeah, any kind of infinite open interval is also uncountable. The reals are uncountable. I mean, the reason that the real numbers are uncountable is because it contains 0, 1 as a subset, right? So if you contain an uncountable subset, then you're uncountable. You know, the complex numbers are uncountable because they contain the real numbers, and so on. But you know, if you can't do it this way, or if you're, you know, if the question tells you to do it in a certain way, you might have to do it by going through this argument here. So, so this argument, by the way, is called Cantor diagonalization. So this is the trick we did here. So it's named for a guy called Cantor who came up with this. And a third way to show something's uncountable is just to find a bijection from A to a known uncountable set. Okay. So, by the way, if this trick seemed like really weird to you, you're kind of in good company, because like when Cantor came up with this concept of countable and uncountable sets, actually most mathematicians thought it was complete garbage. You know, they thought this was some sort of a trick that I think people thought like, of course, two infinite sets, they have the same size. They're both infinite. Like there's no bigger infinite set than an infinite set, right? Whereas this argument proves that, you know, the real numbers are bigger than the natural numbers. And so people thought that was kind of nonsense. It actually probably partially contributed to Cantor ending up in a mental institution at some point in his life, because, you know, all of his colleagues like just tried to discredit his work. Like there's papers written, Cantor is wrong, and this is why, kind of thing, which would be kind of, yeah, that would get to a person, I think. But okay. here's a weird question. Oh, first of all, maybe I need to introduce a little bit of notation. So we often write the cardinality of the natural numbers is something called, so it's represented by a symbol that I can't really draw, but if you look in the notes, it's some sort of a weird looking X. This is called aleph. So this is the Hebrew symbol aleph, and the 0, we say naught. So if you see this symbol, what it means is the cardinality of the natural numbers, or the cardinality of any countable set. So for example, you could see like Z, the cardinality of Z is aleph naught. Whereas the cardinality of the real numbers, or for example, the cardinality of 0, 1, we write as C. Okay, where the C stands for continuum. So it definitely doesn't stand for countable, because these sets are not countable. Here's a kind of trippy question. So does there exist a set? So what we've kind of established is that we've kind of, in some sense, even though, yeah, I don't want you to really think of these totally as numbers, but we've sort of shown that the continuum is bigger than aleph naught in some sense. There's more real numbers than there are natural numbers. But if this is bigger than that, a natural question is there something in between? It doesn't feel like it, right? But does there exist a set X such that the cardinality of X is bigger than aleph naught? Or maybe everything here looks like an X. So let me call it A. A set A such that it's bigger than that, but smaller than the continuum, smaller than the set of real numbers. So this is something called the Continuum Hypothesis. Maybe let's do a vote. Who thinks that there should be such a set of size between the naturals, the size of the naturals and the size of the real numbers? Yeah, show of hands. Okay, 2. How about there shouldn't be such a set? And how about this is a stupid question? Votes for this is a stupid. Okay, yeah. As usual, you're allowed to vote twice as long as one of your votes is that one. But it turns out actually the third option, okay, maybe I shouldn't say it's a stupid question, but it's a question we can't answer. Not because we're not smart enough to answer it or something. We're actually smart enough to know that we can never, in some sense, we can never answer this question, and we know that we can never answer this question. Although maybe never is kind of a strong word, but this is a proven fact that the continuum hypothesis, it cannot be proved, and it also cannot be disproved using the axioms of set theory. Okay, and the axioms of set theory, this is the whole, I mean, I don't expect you to know what this means, but what you should take away from this is, so all of mathematics is based on what can you prove from the axioms of set theory. Basically, that's the foundation of all math. So basically, this question, as far as we know, there's pretty much no way to answer this question. So if you assume that the answer is yes, that this set A exists, it will not lead to a contradiction. So it's completely consistent with the foundations of mathematics. There's no, if you assume that this set A exists, there's not going to be any problem that occurs from that. So we can, so for all we know, it could exist. But on the other side, if we assume it doesn't exist, there's also no contradiction. So we sort of know that there's sort of no way of knowing the answer of this question, which is a bit weird. Okay, let me prove one more thing for you, and then we'll be done. So this is theorem 8.9.1. So let A be a set So what I want to show is that the power set of A is always bigger than A. Do you remember what the power set is? Maybe we don't, but let me write the statement to the theorem, then I'll remind you what that is. So what I want to prove is that there does not exist a bijection from A to the power set of A. So this is maybe good review from chapter 3, right? Remember, the power set of A is the collection of all B such that B is a subset of A. Okay. So in other words, what this is saying is that if I take a set, it could be an infinite set, right? So okay, this is kind of obvious if A is finite. So if A is finite, then A has some size, and then like let's say it has size n, and power set of A has size 2 to the n, and 2 to the n is always bigger than n. So it's kind of clear that if you have a finite set, this is big. The power set is bigger than A. But it's kind of if now we're dealing with infinite sets, it's not so obvious, right? If I take the power set of the naturals, that's bigger than the size of the cardinality of the naturals. So this is kind of similar to the diagonalization trick, although there's not really a good picture for it. So we're going to go by contradiction. So if I'm proving this by contradiction, what should my next sentence probably be? Yeah. Exactly. Yeah. So I'm going to assume, so what I want to prove is that there isn't a bijection. So I want to negate that statement and assume it, and then I want to get a contradiction at the end. So suppose that f, so it's a function from A to the power set of A, is a bijection. So this is going to be a very similar trick to before. What I want to do is show that I want to get a contradiction by showing that f could not have been surjective. So I want to find something in the power set of A which is not equal to, the image of any element of A. So I want to find something in the power set which nothing maps to under F. So this time it's going to be actually almost kind of easier. So here's the trick. So I'm going to let Y be the set of all x in A such that x is not an element of f of x. Okay. So note that so you really have to be good with your set theory notation here, right? To know that what the heck this means and why does this make sense. But for every x in A, f of x is a subset of A, right? Remember, because f of x is an element of the power set, so f of x is a set, right? It's a subset of A. So writing that x is not an element of f of x makes sense because f of x is a set, and we can write this, right? That x is not an element of f of x. Okay. It's a little bit abstract, but so my point here is I want to show that this is not in the range of f. So claim y is not in. So I think this was our notation for range, or something like that, the range of f. So so we're kind of going to do this part by contradiction as well. Suppose there exists some z in A such that f of z is y. Okay, and I want to get a contradiction. So I'm kind of going to break this proof up depending on whether z is an element of y or not. So suppose z is an element of y. Case 1. Okay. Well, if z is an element of y, well then, I mean, z is obviously an element of A such that z is an element of f of z, because f of z is y. So writing that z is an element of y is the same thing as writing that z is an element of f of z, because f of z is y. But then if I know that z is an element of f of z, then z doesn't satisfy the criteria of being an element of y. So the fact that, so since z is in f of z, z is actually not in y. But that's a contradiction, because there can't be a, z can't simultaneously be in y and not in y. So that's a contradiction. And case 2 is almost the same thing. So case 2, suppose z is not in y. Well, then z satisfies the criteria of being in y. So then z is in y, but that's a contradiction again. Okay, so that proves the claim. Because if we assume that something f of z is y for some z, no matter what, we get a contradiction. And this proves the theorem. So this proves that f is not surjective, which is a contradiction, which proves the theorem. Okay. This is quite an abstract proof, I think. But what this gives you is that, so we know about finite sets, we know about countable sets, and then we know that the reals are uncountable. You could ask, are there even bigger sets than that? And this allows you to construct bigger and bigger sets, right? So right, we have kind of some sort of scale from small to large sets, where the smallest sets are finite sets, right? So this is like for some n. Then you have countably infinite, which is like things that have the same size as the naturals. Then you have the continuum, which has things like the interval 0, 1, the reals, but also the power set. So out of interest, the power set of the natural numbers has the same size as the reals. But then you have things which are even bigger, right? You have like the power set of the reals, which is bigger than the reals. But then you can also take like, or for example, the power set of the naturals. Or you could take like the power set of the power set of the power set, and these things are getting bigger and bigger. So there's sort of, by taking power sets, you can make a set. You can take a set and get a bigger set. So you can always find a bigger set, essentially. So if you take the power set of the power set of the power set of the naturals, that's even bigger than the power set of the power set of the naturals.